All right, today we are diving into something super interesting, the secret life of a drug inside your body. It's this incredible science called pharmacokinetics, which is really all about what your body does to a drug from the second you take it. Let's jump right in.
So think about it. You swallow a pill and, a little while later you hopefully feel better. But what actually happens in that black box of time between swallowing it and feeling its effects? It seems so simple, but it's really this complex, fascinating adventure that our bodies navigate every single time.
Well, it's not magic, even though it can feel like it. There's a whole process, a four-part journey that scientists call ADME. And that's an acronym that stands for absorption, distribution, metabolism, and finally, excretion. This four-step framework is basically the roadmap we're going to follow to understand this entire trip.
Okay, let's start at the beginning. The A in ADME, absorption. Before a drug can do any good at all, it has to get into your system. And this is its first and, you could argue, one of its biggest challenges.
So what is absorption really? In simple terms, it's the drug's big move from wherever you took it, say your stomach if it's a pill, across a biological barrier and into your bloodstream. You can think of it like the drug trying to get its ticket punched to get on the body's superhighway.
But here's the thing, getting that VIP pass isn't a given. A whole bunch of things can totally change how quickly and even how much of a drug gets absorbed. We're talking about everything from the acidity in your stomach to how much blood is flowing to your gut to whether or not you just ate a big meal. This is exactly why some pills have those specific instructions, like take with food or on an empty stomach.
So how does a drug molecule physically do that? How does it cross that barrier? Well, it has a few tricks up its sleeve. The most common way is just by kind of slipping through the cell walls. That's called passive diffusion. But sometimes it needs a little help. It might hitch a ride on special carrier proteins, or in some cases, it actually gets actively pumped across, which costs the body energy to do.
This brings us to a really important idea, bioavailability. This is basically the scorecard for absorption. It's the percentage of the drug you took that actually makes it into your bloodstream in its original active form. So if you take a 100 milligram pill, but only 70 milligrams get into your blood, well, its bioavailability is 70%.
And how do we even know that? Well, scientists can actually map this out. They take blood samples over time and plot the drug's concentration, which creates a curve. You can see how it rises, hits a peak, and then starts to fall as the body gets to work. The total space underneath that curve, they call it the area under the curve, or AUC, that tells them exactly how much drug made it in. A bigger area means higher bioavailability. It's that simple.
Okay, so the drug is in. It passed the absorption test and it's officially in the bloodstream. So now what? Well, now it's time for stage 2, the D in ADME, distribution. This is where the drug basically goes on a grand tour of the body to get to where it needs to be.
Distribution is just the official name for the drug traveling out of the bloodstream and into all the different tissues and organs. That highway analogy is perfect. The bloodstream is the interstate system, and all those little drug molecules are like cars, heading off to all sorts of different destinations.
Now, here's a super cool detail. A lot of these drugs don't travel solo. They can't. They need to hitch a ride by latching onto proteins that are already floating around in our blood. The big one is a protein called albumin. You can think of it as the body's taxi service, picking up drug molecules and chauffeuring them all around the body.
And this is the absolute key takeaway right here. It's only the unbound drug, the molecule that has hopped out of its protein taxi, that is actually free to leave the highway, get to the tissues, and do its job. Any drug that's still bound to the protein is just along for the ride, temporarily inactive until it gets dropped off.
So, our drug has been delivered. Mission accomplished, right? Not quite. Now it has to be processed. This brings us to the M in ADME, metabolism. And for this part of the journey, we make a major pit stop at the body's master chemical processing plant, the liver.
The whole point of metabolism is basically to change the drug so it's easier to get rid of. See, most drugs are designed to be lipophilic, or fat-soluble, which helps them get through cell walls during absorption. The liver's job is to run them through a chemical car wash and turn them into hydrophilic, or water-soluble products that can be easily flushed out of the body by the kidneys.
But check this out. This is where it gets kind of mind-bending. Some drugs are actually designed to be totally inactive when you take them. They're called prodrugs. It's your body's own metabolism, right there in the liver, that flips a switch and activates them. The classic example is L-DOPA for Parkinson's disease. It's inactive until the body turns it into the active neurotransmitter dopamine. How cool is that?
This whole metabolic process generally happens in two main stages. You can think of it like a two-step cleanup process. In phase 1, the liver's enzymes make a first chemical change to the drug, kind of like prepping it for disposal. Then, in phase 2, they attach a big, bulky, water-soluble tag to it. This makes the drug totally unmissable, basically screaming, "Get rid of me," to the kidneys.
And just to give you an idea of what's going on, this is a map of just how insanely complicated phase 1 is. It's like a huge biochemical circuit board inside your liver. Each of those paths is a different reaction run by a specific enzyme. And this is so important because if one drug is hogging a pathway, another drug you take might get stuck in a traffic jam, which can lead to some really dangerous interactions.
Okay, so we've got this incredible, complex system in the liver for processing drugs. But what if I told you that that system is totally different for you than it is for me? This is where the journey gets really personal, because your own biology can completely rewrite the rulebook for how you handle a medication.
Age is a massive one. For a newborn, their liver enzymes are still kinda learning the ropes. They're immature and just can't handle certain drugs. That's what led to the tragic gray baby syndrome with an old antibiotic. On the flip side, as we get older, our liver function naturally slows down, which can make drugs hang around in the body a lot longer than expected.
And it's not just age. Oh no. All sorts of things can tweak the dials on your metabolism. Being pregnant can actually rev up the metabolism of some drugs. And, as you'd expect, conditions like liver disease, or even things you might not think of, like an overactive thyroid or poor nutrition, can dramatically change how your body processes medication.
But maybe the most powerful factor of all, your own DNA. Just look at this example with the tuberculosis drug isoniazid. Because of your genes, you could be what's called a slow acetylator or a rapid acetylator. If you're slow, the drug can build up to toxic levels and cause nerve damage. But if you're rapid, your body produces so many byproducts that it can damage your liver. It's the exact same drug, but with two totally different, serious risks, all dictated by your personal genetics. So you're probably thinking, wow, with all these differences, absorption, proteins, and especially our own personal metabolism speed, how on earth do doctors get the dose right? Well, they do it by translating this whole ADME process into a few key numbers.
One of the most important numbers they use is called the half-life. It's just what it sounds like, the time it takes for your body to get rid of half of the drug in your system. This is the whole reason you take some pills every 4 hours. They have a short half-life, while other pills might last you the entire day.
And tied right into half-life is this idea of clearance. This is basically a measure of how good your body's cleanup crew is, how fast your liver and kidneys can scrub the drug out of your blood. Someone with high clearance gets rid of a drug much faster, and doctors have to account for that. And this, of course, brings us to the final letter, E, for excretion, the drug's final exit from the body.
So from the moment a drug gets in to the moment it leaves, its journey is anything but simple. And as we've seen, it's a deeply personal journey, shaped by our age, our health, and our own unique genetic code. All of this understanding is pushing medicine towards a really exciting future, one where treatments are no longer one size fits all, but are instead tailored perfectly to your body's own unique journey.